Tune in for a tale, words that set sail.
Digital Splendor, Literature Illuminated.
Welcome to The Explainer. Today, we are diving headfirst into one of the most mind-bending ideas in all of science, Einstein's theory of relativity. And we're going to do this together, following the exact trail of breadcrumbs, the logic that Einstein himself laid out for us, on a path that literally reshaped our understanding of the entire universe.
I want you to think of this as a detective story in 5 parts. We're going to follow the clues, just like Einstein did. And our very first clue, well, it's a deep, deep contradiction right at the heart of physics. A single loose thread that, when he pulled on it, would unravel everything we thought we knew about reality itself. You know, Einstein actually began his own popular explanation with this very quote. It was his way of sending a clear message. Forget about making it look pretty, just focus on the raw power of the idea. It's not about how it looks, it's about what it shows us. So let's get right to the heart of it.
This was the question that basically broke physics. See, at the dawn of the 20th century, 2 of the bedrock principles of the universe, one, an everyday rule you see all the time, and the other, a cosmic law, well, they were on a collision course, and something had to give.
So here's the problem. Physics seem to have 2 completely different rule books, one for common sense for everyday motion and a totally different one for the cosmic laws that govern light. Now, separately they work perfectly, but when you try to put them together, they created a paradox that threatened to bring the entire structure of physics crashing down.
On one hand, you've got simple common sense, right? If you're on a moving train and you throw a ball forward, the speed of the train and the speed of your throw, they just add up. Simple. But on the other hand, you have this cosmic law that just defies all common sense. The speed of light is always the same. It doesn't matter if you're chasing a beam of light or running away from it, you will always measure its speed as the exact same number. Now, these 2 ideas, they cannot both be true in the same universe. So which one is wrong?
Well, this is where Einstein's genius really shines. He didn't try to break either rule. Instead, he questioned the very foundation they were built on. He realized the problem wasn't with the laws of physics, it was with our deeply flawed, totally human assumption about what it means for 2 things to happen at the same time.
Think about it. We all just assume that now is now for everyone, everywhere. Like there's this giant universal clock just ticking away for the whole cosmos. Well, Einstein was about to show that this is completely, utterly wrong. And he did it with a really simple story about a train and 2 bolts of lightning.
So for our observer who's just standing still on the ground, it's super simple. He's standing exactly in the middle of where 2 lightning bolts strike. The light from both of those flashes travels the same distance and hits his eyes at the exact same instant. So for him, he can say with absolute confidence, yep, those 2 things were simultaneous.
Okay, but now things get interesting. Let's put an observer on a really fast-moving train. At the exact moment the lightning strikes, she is also perfectly in the middle. But unlike our friend on the ground, she's moving. She's speeding toward one of the lightning strikes and away from the other one.
And here it is, the solution to the whole paradox. Because she's moving toward the light coming from the front, that light has less distance to travel to reach her eyes. It gets to her first. So from her perspective, the front lightning strike happened before the rear one. I mean, the takeaway is absolutely staggering. There is no universal now. Time itself flows differently depending on your motion. This is how the speed of light can be constant for everyone, because time and space themselves literally stretch and shrink to make sure it is.
Now, solving that paradox of light, that was a huge victory. But this special theory of relativity, as he called it, had a catch. It only worked for things moving at a nice, constant, steady speed. It completely ignored the real, messy universe of changing speeds, of acceleration, and the biggest accelerator of them all, gravity.
Tackling this question would demand an even more radical idea. It was a leap that would take Einstein from his special theory to his absolute masterpiece, the general theory of relativity.
We all feel gravity, right? We think of it as this field the Earth creates, pulling everything down. But for centuries, there was this deep, peculiar clue hidden inside this everyday force that everyone had kind of missed.
So here's the key clue. Galileo famously showed that if you get rid of air resistance, a feather and a cannonball fall at the exact same speed. Gravity accelerates everything equally. Now for Newton, this was just a weird coincidence. But Einstein? He saw it for what it truly was,
a profound link between an object's resistance to being pushed, its inertia, and how it responds to gravity. Why on earth should those two very different things be perfectly exactly equal? This so-called coincidence was the key to the entire mystery.
Pondering this very connection led Einstein to what he later called the happiest thought of my life. Just a single, simple image that would change absolutely everything.
Okay, picture this. Imagine a physicist inside a closed box, like an elevator, just floating in empty space. No gravity, he's totally weightless. Now, imagine a rope is attached to the top and starts pulling that box up with a constant acceleration. What would he feel? Well, he'd feel his feet planted firmly on the floor. If he dropped a ball, it would fall straight to the floor. From his perspective, everything inside that box would behave exactly as if it were just sitting on the surface of the Earth.
And this leads to the earth-shattering question. With no windows to look out of, is there any experiment he could possibly do inside that box to tell the difference?
Einstein's answer was a definitive, resounding no. From inside the box, the two situations are completely identical, indistinguishable. He could not tell the difference. This incredible revelation is called the principle of equivalence. The effects of gravity and the effects of acceleration are not just similar, they are fundamentally the exact same thing. So, if gravity and acceleration are the same thing, then what is this thing we call gravity? Well, this leads us to the final, spectacular revelation of Einstein's theory. Einstein realized that Newton's idea of a spooky action at a distance, some invisible force pulling things across empty space, that had to be wrong. Gravity isn't a force in the universe, it's a property of the universe itself.
And here it is, the final revelation. Mass doesn't create a force. Mass tells space and time how to bend. And that curved landscape of what he called spacetime, in turn, tells mass how to move. The Earth isn't being pulled by the sun's gravity. The Earth is simply following the straightest possible path it can through a universe that has been warped and curved by the sun's immense mass. What we feel as gravity, it's just the shape of the universe itself.
Now, this wasn't just some pretty picture he cooked up. It was a real, testable, scientific theory. And it made a shocking prediction. If space itself is curved, then even something without mass, like light, should bend when it passes by a massive object like the sun. And Einstein calculated the exact amount of deflection, a tiny but measurable 1.7 arcseconds.
And so, during a total solar eclipse in 1919, teams of astronomers raced to take pictures of the stars near the blacked-out sun. And when they developed the photographic plates, the results were unmistakable. The stars' positions had shifted, the light had bent, and it had bent by the exact amount Einstein had predicted. And just like that, overnight, he became the most famous scientist in the world.
And this really is Einstein's true legacy. It's not just the answers he gave us. It's the quality of the questions he left behind. By showing us that space can bend, that time can slow, and that gravity is just geometry, he revealed that our everyday reality is just a tiny sliver of a much larger, stranger, and more wonderful universe than we had ever dared to imagine.